Guenther.
Thank you. I would also like to thank the CoRoT science team for making this whole work possible. And I'm speaking today about a discovery made by CoRoT and the science team about a planet which has it's orbiting a star of 1.4 solar masses. Now, why is this interesting? If you look at the literature, then you see, okay, this is stellar mass here, and the fraction of planets, massive planets, and this is increasing. So if you think between 1.4 solar masses, the number of, say, hot Jupiters is much larger than for solar-like star. So it's boring. But wait a second. All these data points here are based on radio velocity surveys of giant stars. So actually, there are no close-in planets here in this diagram. So actually, we don't know if we have any close-in planets around stars more massive than the Sun. Why is this interesting? First of all, let me point out that the lifetime of the disk, as measured by Spitzer, for stars more massive than the Sun, is much, much shorter than for solar-like stars. So you have little time to form a planet, and you have even less time to let it migrate inwards. Obviously, because we found planets at large orbital distance, there must have been enough time to form them, but maybe there's not enough time to migrate them inwards. So by surveying for close-in planets around stars more massive than the Sun, you constrain the speed of migration. The second thing which is very interesting is that, of course, if you go to, say, A-type stars, they are far brighter than the Sun. They have far more UV radiation, so the amount of evaporation is much, much larger. And by looking for stars or planets around stars more massive than the Sun, you also constrain how the evaporation of planets works. Okay, now is CoRoT able at all to detect such planets? And the line here shows the depth of the transit of CoRoT 7b. Here is the spectral type. And CoRoT in principle has the sensitivity to detect Jupiter-like planets of stars as early as B-type stars. So it's actually for CoRoT relatively easy to find planets around A-type stars, and that's what we would like to do. And here I would like to introduce you to an object which I call CoRoT-35. And this is the transit light curve. Well, not very spectacular. You see a nice transit, very nice. But of course, now the big work is excluding the false positive. If you see a transit, that doesn't mean you have a planet. And there are lots of steps, and this is basically the work of the CoRoT science team. And I would just like to concentrate on the last bits. What you do is a detailed modeling of the light curve and so on. There you remove a lot of these false positives. You do the high resolution spectroscopy to make sure that you really have a solar-like stars. And you do radio velocity to constrain the mass. And then in the end, you do observations during transit and out of transit to make sure that you have really the transit on the target, which we did. In this case, Hans was, of course, involved and confirmed that really the transit is on the star. But wait a second, we also have made a similar survey for CoRoT objects where we did AO imaging, so looking for additional stars within 1 arcsecond of our targets. Now you can say it's very unlikely that within 1 arcsecond of a target that there is an object. Actually, the probability, if you go to the statistics of binaries and background stars, less than 10%. We did this, and the real number is 30 to 40% of our candidates had stars within 1 arcsecond. So you actually need AO imaging to remove the false positives, which we did. And this is an image taken with a large binocular telescope of our targets. Actually, we found 2 stars, but when we made a more detailed studies, these stars are at too large distance and actually too faint to be false positives. So really the transit is on target, so we really have a transiting planet here. Now here are the basic parameters. Of course, we were originally looking for planets around A-type stars. Now we have one around an F-type star. Again, of course, relatively rapidly rotating. Unfortunately, we got from the radial velocity, because it's rapidly rotating, only an upper limit of the mass, and but there's more to say about it. Davide already introduced you to the Rossiter-McLaughlin effect and also to the what I would call Doppler imaging of planets or time-resolved spectroscopy, where you observe the shadow of the planet crossing the stellar disk. So I don't have to repeat it. Davide explained the method to you. First of all, let's do the classical Rossiter-McLaughlin measurement. Here is basically these dashed lines is the beginning and the end of the transit here. And these are the out-of-transit data, and this the in-transit data. And these are two different transits observed with two different telescopes, and you see that there is a significant difference in radial velocity during transit than out of transit. And actually, out of transit, the variations are very small. And we did this experiment twice. Now, you're used to Rossiter-McLaughlin observations, where you see here a nice curve, and now you have an absolutely flat line. What does it mean? And of course, we can also do this time-resolved spectroscopy. This is actually the only known transiting planet around an A star, which is known today, which is WASP-33. It had the same problem, rapidly rotating star. We took 300 radial velocity measurement, didn't get the mass of this planet, but we used time-resolved spectroscopy, in this case with 3 different telescopes. And we see here very nicely, always at the same point during the transit, say the shadow of the planet crossing the stellar disk, which you see here nicely. By the way, this is an A-type star, and all the rest of this is stellar oscillations. But I'm not speaking about this. And this is the data of this object, which I nicknamed CoRoT3-KASC7. You see also the hump after subtracting the average line profile. And now as a black dot, you see the signal of the planet, which is constant, which means one thing: the planet is actually orbiting in this direction. This is the spin axis of the star, and so it is in a polar orbit. That's a very rare case. You have misaligned objects are very well known, but actually a polar orbit, that's a very unusual situation. So it's a transiting planet in a polar orbit, and this is of course not the only planet that CoRoT has found around a star, which is more massive than the Sun. And here's actually the table of all the publicated planets already. Here's this new one. It's also around a star which is more massive than the Sun. Okay, it's not an A-type star, but it's at least 1.4 solar masses. And then you're saying, oh wow, CoRoT found so many planets around stars more massive than the Sun. So the number of close-in planets is huge. But of course, we have to look at the statistics of how many A-type stars are in the CoRoT sample, which is 16%, how many F-type stars, 35%, and compare it roughly with the number of planets that CoRoT found. Of course, this statistic, we are still working on it, and but you see one thing, CoRoT found, in fact, a lot of planets around F-type stars. Maybe less than 5% of the CoRoT planets found around A-type star. Maybe there's 1 or 2 or maybe none, but at least this is a small number. And in the CoRoT sample, there are a lot of A-type stars. So very cautiously, we can say that the number of close-in planets around A-type stars is low. Of course, the statistics still has to be completed, but there is the first impression that A-type stars have a lot of planets at large orbital distance, but few planets at close distance. And the explanation is formation of planets, even giant ones, is quick, but the migration time must be so slow that simply the planets have no time to move inwards. And here's basically our results. We actually focused on a survey for A-type stars. We found 19 very nice candidates. Unfortunately, most of them, oh, then I'm pretty much in time. You have more time for coffee. And we have 19 candidates we followed up. And remember, the size, the depth of a transit of an M-type star is the same as a Jupiter-like star. And we found lots of transits, so we have the sensitivity. It's only that the stars don't have the planets. And that means that there must be really a lack of close-in planets around A-type stars. And such objects must be very rare. And we can say one thing, these rapid or drastic increase of the frequency of planets, which is observed around, say, stars more massive than the Sun, that is seen for planets with large orbital distance. We don't see for the planets at small orbital distance, so there is a lag. There are some, but there is a lag, and this lag seems to set in really at the spectral type of A, or let's say at 1.5 solar mass stars, because between 1.1 and 1.5 we still find a lot of planets, and that's where I would like to stop. Thank you very much.
Yeah, thank you. Questions to this?
There is some evidence that about 20% of A-type stars have planets around them, and this comes from the Kepler data.
Yes.
I don't have time to explain where this evidence comes from. But in a nutshell, these seem to be planets which co-rotate with the star. You know, the orbital period of the planet seems to be about the same as the rotation period of the star. Now, this is an explanation. It's the only explanation I can find for certain features I've found in the Kepler A star periodigram. Whether it's true or not, I don't know. But at least it can be easily falsified.
That is absolutely true. What we did was a dedicated survey for orbital periods, say less than 4 days, because these are the ones which we can confirm with radio velocity in principle. And if it's on the orbital period of an A-type star, these would be planets with orbital periods of less than a day, which is a possibility, but at least in the CoRoT data, we didn't find such planets, but let's see.
So for CoRoT-35b, do we see any nearby stars that could have skirted the architecture of that system? Do we see any nearby stars?
Well,
I mean, that would be sufficiently, of course they are, but are there stars sufficiently close to the host star that would have resulted in dynamical interaction, that would have made in the end this planet get this polar orbit? Or
no. Unfortunately, the distance is too large to move this planet via Kozai mechanism inwards or something. And because I didn't show it in detail, we have multicolor photometry on these closest stars, and they are actually background objects. They are not binaries, but with WASP-33 you are right. It is a binary, and we recently found a third one. So there are 2 other stars. Now, one problem is the binary fraction in A-type stars is very, very high. Whether this one example, that it is a binary, means something, I don't know. But this one seems to be single unless that there is another star at large distance, but not a close-in one.
So any idea why this planet has a polar orbit?
No. Actually, yes. It's a longer discussion, and that is an idea that was pointed out to me by Doug Lynn, and he said, what you measure actually is not really the spin axis of the star, but only in principle the motion of material on the stellar surface in this path of the transit. And he said maybe that there is some, like the giant cells on the Sun, some motion on the star, and this is faking that the spin axis. And he said, you should do one thing, repeat Rossiter McLoughlin observations of the same objects after 10 years. If you see a change in this angle, then you know that this is some bizarre surface feature on the star. If you don't see a change, okay, you don't know. But I was so convinced that I said, as an observer, we should do this. And we actually tried. And there's something in this idea which I like.
Okay, thank you. Eike, there was another question here.
Did I understand you right? In your follow-up observations with the adaptive optics, if you see a companion star, do you then classify this as a false positive? Because that seems premature.
It could, of course, be true that lots of Well, simply that binary stars have more planets than single stars, then of course this occurrence would be just a coincidence. And what we need is really proving that the transit is really on the primary and not on the secondary, which is a little bit more tricky because then you need the AO imaging during the time of the transit, and actually we started doing this data. I'm very keen to see the results, but there is a possibility that actually these are not false positives, but that stars with planets are very often binaries with a second companion at several 100 AU distances. That's a possibility.
Okay, thank you.
If we see a second star, usually it moves down in the list of the priority, but it's absolutely correct that the binaries we see, that there is a possibility that still the transit is on the primary, and this is a transiting planet in a binary star. If the transit is on the secondary, then of course it is just an eclipsing secondary. And could be, but then of course, depending on the size of this object, it has to be a relatively large object. So let's say either massive planet or really binary. It's relatively easy to find this out, and we are still working on it, and we have already the data, but it's true.
Okay, one more question was at the far end here.
I'd like to go back to Louis' suggestion that 20% of A stars should have hot Jupiters. It turns out that there's not really any evidence in terms of transits of these hot Jupiters around the A stars, and certainly not to the tune of 20% of them.
No. Maybe you missed it. It is 20% of the stars that CoRoT observes are A-type stars. Less than 5% of them less than 5% of the CoRoT candidates are A-type stars. So if you make the statistics, the frequency of hot Jupiters is at least a factor of 4 smaller than for G-type stars. It's not 20%. 20% is the sample.
That wasn't the point. Louis was suggesting that, say, 20% of A stars have hot Jupiters.
No. I said the opposite.
Yes.
Sorry.
I was agreeing with you. It's okay.
No, it was the opposite. The number of planets around A-type stars which are transiting or with short periods is very, very small.
Okay, thank you. No more questions? Oh, here.
You ask. I thought we had no time, but if you ask, I'm a bit puzzled. I'm a bit puzzled by your definition of A-type star, and it's a bit tricky to me because for me, a 1.3 is definitely not an A-type star generally. It begins around. No, but it's important because it begins around, let's say, 1.6, 1.7, and then you are in the middle of the instability strip. So I guess it will be harder for you to define to find planets around stars which are in a large number pulsating with a high amplitude and so on. You see what I mean? So your statistics is a bit puzzling.
That is the answer why these candidates haven't converted into planets. It's these oscillation which mess up the things. Yes. And that is also the answer why we haven't determined the mass of CoRoT of WASP-33. The amplitude of the oscillations are as large, if I may turn it into mass of a planet, as about 1.5 Jupiter masses. That's the amplitude of the oscillations. So that means it's very difficult to go below 1 Jupiter mass, even if you have 300 spectra, because you have the oscillation frequency. Luckily, there are several months of most observations where we know this frequency, and you have to subtract this in order before you see the planet. The same with CoRoT, you have to subtract the oscillations before you can see the planet. That's a problem.
Okay, thank you then, the speaker.